sharing now, or it's okay?
I mean, it's your call. You can keep the screen like this only because you will be the first speaker, or you can stop the sharing. That is up to you.
It's fine if I can keep the screen then, just to avoid doing this again.
Okay. So the recording has been started, isn't it?
Yes. So what we'll do is, once you actually start, we'll trim up this portion. We'll remove this portion.
Yeah.
Once the actual meeting starts, only that recording will be kept and sent to you.
Yeah, all right.
So from this moment on, my camera and my mic will be off. We will be there in the background.
All right.
In case there is any issue, you can contact me on WhatsApp. I'll immediately respond.
Yes, all right. Okay, that's fine.
Right.
That's fine. Thank you very much.
Have a wonderful webinar. I'm really glad, and may this be the first of many more to come.
Thank you very much. Really appreciate your hard work. Thank you.
Okay.
So, Mujtaba, we will start at 10 sharp, right?
10, inshallah, inshallah.
Yes, all right.
We'll just wait for participants.
Red cells antigen variant. Khalid Al Hasibi screen. കുറേ പേരുണ്ടല്ലോ.
Hello.
أهلا دكتور زينب، how are you؟
الحمد لله دكتور، كيف الحال؟
الحمد لله تمام.
Good morning. How are you?
Good morning, Doctor. How are you?
Alhamdulillah, fine.
Alhamdulillah.
We are waiting for some participants. Like we will start
Okay.
at 10 o'clock. Yeah.
Hopefully we have more, many people to attend.
Yes.
Inshallah.
Yes. Happy Oman. ও ঠিক আছে, ওই যে এখন ছাত্রদের পরে দেখা করে। হ্যাঁ ঠিক আছে, এখন না পরে। হ্যাঁ আচ্ছা ইয়ে হ্যাঁ যাবো, ওদের বলে যে যাবো একটু মির্গা আমি।
Yeah, this is causing that crowd. يا ربي الناس تصدقي انك انت حاطيتي
السلام عليكم ورحمة الله. So shall we start the meeting now?
I think.
Hello.
Yes.
Yes, doctor, you may start now.
Okay, I need just to. Okay. Now the vote is clear. So, ladies and gentlemen, Assalamu alaikum and very good morning to you all, to our first Asian Association of Transfusion Medicine webinar, Oman chapter. The AATM is a manifestation in blood transfusion medicine from Asian countries to work together towards finding solutions for their common problems in the spirit of friendship, trust, and understanding, and to create an order based on mutual respect, equality, and shared benefits. The primary objectives of the AATM is to accelerate the scientific progress and common standards in blood transfusion medicine and member states in the South Asian region. And we are part of the AATM since February 2020 in order to achieve high standards in blood transfusion services. Before starting the session, I would like also to thank the president of the AATM, Dr. Chowdhury, and the Secretary General of AATM and Vice Chairman, Dr. Ananda, for their support and their willing to include Oman as part of this organization and to propagate a message of safe blood transfusion. A special thanks to the logistic team, Dr. Ankit and Dr. Aikaj, who have provided this communication platform and connected us to the ward. As the president of the AATM Oman chapter, I would like to thank the lead members, Dr. Mujtaba Al-Lawati, Vice President, AATM Oman chapter, and Dr. Shadia Khan, the secretary, for the full support they gave to fulfill the vision and aims of the AATM worldwide. Now I would like also to welcome a very active member of the Central Blood Bank and Head of Laboratories, Dr. Khalid Al-Habsi, to present his topic on red cell antigen variants in patients with sickle cell disease. Dr. Khalid, the floor is yours.
Thank you. Thank you very much, Dr. Zainab, and welcome to all the attendees in this webinar. First, I would like to thank the team at the AATM for this wonderful chance to share with them this presentation. And since we are having two presentations today, I'll try my best to make sure to make it as short as possible. So my first presentation is actually about red cells antigen variants in patients with sickle cell disease. And the main objectives I'm going to discuss in this presentation. First, we'll give a general background about sickle cell disease and the risk of alloimmunization. Few case examples to make it clear how these variant alleles can result in unusual antibody results. And then we'll try to understand the role of molecular genotyping in red cell antigen predictions. Perhaps half of the presentation will include discussion of the study results that was published recently. So we all know that sickle cell disease is one of the most common genetic blood disorder in the world. It's no longer confined to one country or one place or one continent. With all this huge immigration around the world for different reasons, every country nowadays has an issue with management of sickle cell disease patients. And blood transfusions remains one of the most effective management modalities and a key component in the management of those patients. However, it is not without complications. Although blood transfusion have improved the morbidity and mortality, we know that a high incidence of alloimmunization complication is associated with blood transfusion, especially in the sickle cell disease group. And different studies have reported different rates of alloimmunizations. If we look at this table, for example, with different studies from different countries around the world, we can notice there are some variations in the rate of alloimmunization in sickle cell disease patients. And I think that's because of the every country has its unique situations when dealing with sickle cell disease patients. For example, if we take in the UK, we know there is a huge difference between the donor population and the patient population, and that's one of the huge reasons why alloimmunization is high in this group of patients. Alloimmunization in itself is a problem, but it predisposes the patients with sickle cell to more risk, including delayed hemolytic transfusion reactions, even worse, hyperhemolysis if it happens, and overall difficulties in obtaining compatible blood in the appropriate time. Over 2/3 of these antibodies are actually found in the Rh and KIL system, and that's why most countries, including Oman, nowadays we apply the prophylactic approach of providing Rh and KIL matched antigens for our patients. These strategies, although improved a lot in the rate of alloimmunization, however, the risk of antibodies is still high. Some reports presents up to 15% of alloimmunization despite providing phenotype matched blood transfusions. And there are many factors, as I said, for this alloimmunization risk. It's not only the disparity between the donor population and the antigen distribution of the sickle cell disease patient itself. Sickle cell disease itself is a highly inflammatory disease, and the burden of blood transfusion plays also a major role. However, the factor that I want to concentrate in this presentation today is the high degree of antigen variability observed in this group of patients, especially the weak and partial antigen expression. And this is not a new issue when we talk about Rhd antigen, for example. It has been there for many years, even before the era of genotyping is well established. However, nowadays, we have noticed that these partial antigens also happen in other Rh antigens. And the prevalence of the altered other Rh antigen alleles in patients with sickle cell disease suggests that the molecular studies have an emerging role in providing matched blood for sickle cell disease patients. To make this idea more simple to understand, let me present to you a few cases that we have encountered here in our lab. The first case, we received a sample a few years back from the Royal Hospital, one of the major tertiary hospitals here in Muscat, and it was from an 11-year-old post-renal transplant boy. His blood group was ORHD negative. The antibody screen is positive, and the identification panels were all band-reactive with positive autocontrol. That was also positive for IgG. So because we thought that there are autoantibodies, we did an elution study at the beginning. However, the eluate tested showed a band-reactive pattern, and that goes well with non-specific autoantibodies. Next step, we did adsorption study. And due to recent transfusion, we had to perform alloadsorption. The adsorbed serum showed a clear anti-Big C antibody detected mainly by the enzyme-treated cells. The problem here, there are two unusual things in this patient. First, his Rh phenotype is Big C positive, little c positive, and he is Big E and Kill negative, and it's okay if he develops antibodies to Big E and Kill. That's the usual thing. Patients develop antibodies to missing antigens. But now we have an anti-Big C in a patient who phenotypes as Big C positive. Many thoughts will come to mind, including, is this an autoantibody with some specificity to Big C? However, after adsorption, you would expect that all non-specific autoantibodies are removed. So our transfusion advised that this autoantibody warrants some further evaluation for a possible autoimmune hemolytic anemia. However, an underlying anti-C antibody is detected, and genotyping would be really useful to rule out variant Big C. The other unusual thing here is actually this patient is ORHD negative, and 99.9% in some studies, he should be Big C negative. However, he was phenotyped as Big C positive, at least by serology. The second case is quite similar. He's a 40-year-old man referred from Al-Nahda hospital with sickle cell disease and admitted with painful crisis. His blood group is O positive, and he had a positive antibody screen. And his Rh phenotype, again, he was Big C, little c, Big E, little e, and positive, and only Kill negative. However, we could detect anti-little e antibodies in his serum. That was negative, so that it's less likely that this anti-little e is actually an autoantibody. So that's the second case. The third case, quickly, this case happened in other place and time, and this was a 26-year-old lady with sickle cell disease in her first trimester of pregnancy, admitted again with VOC pain. She received multiple transfusions in the past. Her blood group was ORHD positive. Antibody screen is positive. That is negative. So an issue of autoantibodies here is also less likely. The identification panels revealed anti-Big C and anti-Big E antibodies. And looking at her Rh antigen phenotype, again, she was Big C positive, Big E and Kill negative. So she developed an anti-Big C in a phenotype by serology Big C positive antigen. So these cases and more, I'm sure many of you have encountered during your laboratory work in transfusion medicine. This really brings the ideas of the need of molecular analysis to rule out partial antigens. However, we know nowadays it's actually limited. The molecular analysis is limited to reference centers, and it's limited to resolving complex antibody identifications. Perhaps in some Rh typing discrepancies, and fetal Rhd typing and paternal D zygosity and so on. However, fortunately, with time, the molecular studies have been more available and for a cheaper price. Just having a look at the Rhd gene and the Rhd gene, the loci are quite similar to each other in the same chromosome, and they actually are facing each other. The 3' from each locus is facing the other gene. And it is known that when we have Rhd negative, the whole gene is deleted. Usually, in 99.9%, it's associated with big C and big E negative phenotype. So that's important to keep in mind. Again, if you go and have a look at the human rhesus database, which is updated quite regularly, you can find a large number of Rhd variants. If you screen through all of these options of the D antigen, you may find more than 500 variant alleles reported. Some of these variants alleles are quite common and frequently found, and some are very rare. On the other side, the Rhce variant, you can find around 150 or more variant alleles have been reported so far. So this is a free access website usually used by reference laboratories, and it's very useful in looking for such Rhd variants. Having a look at the Rhd antigen, as I said, it's a large protein with this characteristic transmembrane domain, and each one of these colored small circles represents one of the single nucleotide polymorphisms that have been reported in the Rhd gene. I would just kindly ask you to mute your microphones all the time so that we don't have this kind of echoing. Thank you. So again, this is the Rhd antigen gene with many reported single nucleotide polymorphisms resulting in variant alleles. If you have a look at the Rhd antigen, is very similar to this. It's actually 97% identical. There is only a 32 to 35 amino acid differences. And all of these reported variant amino acids mutations results in different forms of variant alleles in the Rhd and also in the Rh genes. Many studies have looked at the differences between doing a DNA-based genotyping red blood cell antigen prediction compared to the usual serological typing that we do every day in the lab. And one of these studies is the study published in Transfusion 2015 by Jessica Cases and her colleagues from Philadelphia, which showed clearly there is a huge difference between the Caucasian blood donor population and the patients with sickle cell disease. If you look here, all of these antigens with the small star represent a significant difference between the two populations of a p-value of less than 0.0001. And it's very clear if you look carefully at the Diffie antigen, for example, Diffie A and Diffie B, much less frequently seen in the patients with sickle cell disease compared to Caucasian populations. even in the big C, for example, in the S. And in most of these antigens, actually, there is a significant difference between the donor population and the patient with sickle cell disease population. And that's what we talk about is one important factor resulting in increased level of alloimmunization in these patients. Now, from all of what we have discussed earlier, it is more clear to everyone that the role of genotyping is really emerging fast, and the antigen prediction by genotyping often detects some variant antigen gene alleles, as we will see when we talk about the study I'm going to present to you. Several studies from the US and Brazil demonstrated almost half to 2/3 of sickle cell disease patients having variant alleles. And when these variant alleles result in alloimmunization, hemolytic transfusion reactions can happen. And this has been reported in some studies in 1/3 of the patients. So the value of complementing serology testing with genotyping is increasingly reported in the literature. So for the remaining time, I would just discuss with you. I would discuss briefly with you the study that was published early last year, April 2020. This study was done in Canada with other colleagues. We initially presented this study in one of the ASH meetings, and unfortunately, when I had to leave, then the other colleagues like Andrew and Ilahi completed the good work, resulting in the publication of this study last year. So this is a retrospective cohort study of sickle cell disease patients treated in a tertiary center in Hamilton, in Ontario, Canada. And it collects the predicted phenotypes and the variant alleles from the red cell antigen genotyping in Ontario, Canada. All patients gave a consent for genotyping for this study. And all patients with sickle cell disease who consented were tested between December 2014 and November 2019. It is important to note that in this center, since 2012, all patients with sickle cell will receive Rh and KIL matched phenotype. And the predicted red cell antigen phenotypes from genotyping data and the serological phenotyping were assessed to help risk stratify sickle cell disease patients for risk of alloimmunization. We also looked at the clinically important disagreements between the phenotype and genotype testing. And all patients with a variant allele causing partial antigen were considered as having an increased risk of alloimmunization. As you will see, many of those patients actually had the GATA1 Diffie mutation or variant allele, and however, those will still be considered as a standard risk, and I will explain this later on. To do genotyping, we had to send AATM samples to the National Immunohematology Reference Laboratory in Ottawa, and the genotyping was done using Progenica system from Grifols. And for the testing, all of these common antigen systems were included, and this system actually will detect the already reported SNPs or single nucleotide polymorphisms. So if there are other mutations in these patients that are not included in this SNPs system, then it may not be detected easily. It may have to go for complete sequencing. So the primary outcome of this study was the number and proportion of patients who had informative genotyping results. And by that, I mean the presence of a variant allele or any discrepancy between the predicted any difference between the genotype, phenotype, antigen variability. So any patients who gave an informative genotyping results That was the primary outcome of the study. Additional outcomes will include the prevalence of the variant alleles in sickle cell cohort study, the variability between genotyping and serological phenotyping in individual antigens, and the rate of elimination as well. So during the study period, as of November 2019, a total of 106 patients were genotyped, and the results were sent back to us. As you can see, this is the demographics and the self-reported ethnicities. The mean age was 24 years old, and around 52.8% were males, and 44% were in the pediatric age group below 18 years. Most of the sickle cell patients were SS type sickle cell anemia. 30% were sickle SC disease and other sickle cell disease genotypes. If you look at the ethnicities reported, around 28% were of Afro-Caribbean ethnic groups. There is West African, about 26.4%, and other ethnicities, including some from the Middle East and Central Africa as well. The disagreement between the serology phenotyping and the genotyping, in this study, 96 patients out of the 106, that's equal to 90.6%, had a variant allele identified by genotyping. Now, the majority of these are actually the Diffie gata mutation, which I will discuss in one slide later on. Around 52 patients, so that's almost 50% of the sickle cell disease patients studied in this cohort, showed some variant allele in the Rh system. Of those 52 patients, some had only Rhd variant alleles, some had only Rhce variant alleles, and 18 patients had both variant alleles in the Rhd gene and the Rhce gene as well. Of these variant alleles in the Rh genes, 30% were homozygous or compound heterozygous, and around 70% were heterozygous. And when we look at specifically at which antigens showed more variability between genotyping and serology, it was the little c antigen and the little e antigen, and followed by the big C antigen. It's interesting to note that we did not find any variant allele antigens in the big E, for example. So little c, little e is more common to find variant alleles in the Rhce antigen, and followed by the big C antigen. And that's very similar to the other reported literature. So our study have in the Rhce alleles have shown several gene mutations, commonly the little c, little e 2001, which can result in partial little c and partial little e. Please note that some patients have not only one or two, they had 3 or even 4 partial antigens detected by doing genotyping. Like this patient, 2 patients at least from Afro-Caribbean ethnicity had this gene mutation, which can result in partial C, partial little e, and HRB negative. And this patient from West Africa, who had mutations that results in partial big C, partial little e, and HRB negative. And imagine how difficult it is to find blood compatible for such patients. In the Rhd variant alleles, several patients, we said around 18 or 22 patients had gene mutations that results in partial D alleles. So in conclusion, and just to save some time, every study has its limitations. So our study was limited by the retrospective nature, and also the sickle cell disease population was 106 patients. But remember, these studies are done in countries where sickle cell disease didn't used to be a big issue some years ago. And unfortunately, we need more and more studies in countries where sickle cell disease is actually a major problem. However, even in this study, it was evident that variant alleles leading to partial antigen expression was found in at least 24% of patients, potentially putting those patients at increased risk of elimination. Again, the GATA1 mutation for the Diffie antigens was very common. It's almost 90% of sickle cell disease patients studied in this cohort. And all of this suggests that the genotyping should be used more routine basis to assist providing matched blood for sickle cell disease patients. However, we should keep in mind some of these variant alleles, especially the ones who have multiple mutations, multiple variant alleles, can be a real big challenge to find compatible blood with the same genotype. I will conclude with one slide just talking about the Diffie antigen phenotype. So the Diffie A negative, B negative phenotype, which is also known as the erythrocyte silent Diffies, is common in patients with sickle cell disease. Unlike other donor populations or other group of patients. And this is depending on the region, the prevalence of this Diffie antigen negativity can be up to 100%, for example, in West Africa, or 80% in African Americans. I think most of the countries, especially here in Oman, we noted that many patients with sickle cell disease are actually Diffie A and Diffie B negative, and this will be presented in a different data. So this phenotype, why it happens? It happens because of a homozygous variant mutation, a point mutation in the Diffie B gene. This mutation results in impairment of the promoter activity of the red cell erythroid cells by disrupting the binding site for the GATA1 factor. This results in the Diffie B being prevented from expression in the red cell surface, but it is not prevented in other tissues. So the patients will be Diffie B negative in the red cells. However, Diffie B antigen can be found in other tissues in this patient. As a result of this, patients with Diffie A negative, B negative phenotype rarely make anti-Diffie B because of this very common mutation that is found in patients with sickle cell disease. With that, I would like to thank everyone very much. And I would be happy to take questions perhaps at the end of the session. And now I think it's Dr. Mujtaba. Thank you very much.
Thank you, Dr. Khalid, for the interesting topic and wonderful presentation. We'll keep the questions at the end of the session. May I now call and welcome Dr. Mujtaba Al-Lawati. He's a science tutor in Oman College of Health Science to enlighten us with his topic on Rhd positive haplotype in a D negative Omani donor. Dr. Mujtaba, the floor is yours.
Thank you very much. Thank you very much, Dr. Zainab. Good morning, ladies and gentlemen. This is Mujtaba Al-Lawati, and as Dr. Zainab said, I'm a lecturer from Oman College of Health Sciences, and I'm going to talk about Rhd positive haplotype in a D negative Omani donor, which is a case study. So as we know, everyone knows that ABO and Rhd blood testing is mandatory in donor. It's also mandatory in patients who are going, of course, for transfusion, and it's also mandatory for childbearing women, especially in pregnant ladies. And it is the second most important blood group in transfusion medicine. And It has more than 50 antigens has been already reported in the Rh blood group system, but the most important the antigen, big C, big E, little c, and little e. And of course, these Rh antibodies are immunogenic, and they can cause hemolytic transfusion reaction and hemolytic disease and of fetus and newborn. And due to this immunogenicity of Rh antigen and mainly the D antigen, so the Rhd testing is compulsory in transfusion medicine. So before I go and talk about the case itself, let me just, to be honest, I beg your pardon if you feel this as a basic for you, the molecular biology, but I believe we have some few levels here, okay? They might need to understand what is the basic of molecular biology, so that's why I'm including this. So the basic of molecular biology, let's talk about the central dogma, is that we have a DNA which is double-stranded in our body, and which is transcribed actually into a messenger RNA. And this messenger RNA, I have one message, somebody saying, raise your voice. I'm not sure why my voice is not clear, though the volume is high. And let me check, please. Let me check. I beg your pardon again. Let me just check the volume here. If I can do something for the volume. No, I have everything high volume. I'm not sure why. Maybe I can just bring the mic closer. All right. I think this will work fine now. So the DNA usually, in order, of course, as we know, the DNA is responsible to give the protein itself. And the Rh antigen is actually a protein which is directly as a product of Rhd gene. So let's take this as a basic, saying what is DNA? DNA is a double-stranded DNA. As DNA is a double, of course, it's a double-stranded, and which is transcribed into RNA. And this RNA is actually single-stranded sequence. And once RNA, of course, once the DNA is transcribed into RNA, this RNA is initially is a premature RNA, which is processed in the cell itself, and then it will become a mature RNA. But what is the specific feature of this premature RNA? Of course, as I said, the DNA is a full sequence of nucleotides, and these nucleotides are transcribed into a single then stranded messenger RNA, and this messenger RNA will have like exons and introns. If you see here, exons and introns. These exons are actually the coding sequence. They are called the coding sequence. These exons are going to be translated into a protein. So as a processing of pre-messenger RNA into mature RNA, these introns will be removed. Okay, so the only what you will get is the mature messenger RNA, which has the exons only. So this is the mature RNA. The mature RNA, one of the features of mature RNA, it has only the exons, and these exons will be translated into a protein. So having this mature messenger RNA translated into a protein, and of course, as we know, protein is full of amino acids. So now, these messenger RNA, now how these are translated into a protein. And again, I said that messenger RNA is a single-stranded nucleotide, actually a sequence of nucleotides. Now, each three nucleotides is called a codon. And this codon will give you one amino acid. One amino acid. So as you can see the table here, so each three nucleotides will give you a codon, and each codon will give you one amino acid. But the question here, now, how the body knows, or how the cell knows this is the start of the protein and this is the end of the protein. The answer for this, now for any start of protein or protein synthesis, the codon is always OUG, O-U-G. So that's called the starting codon, which is OUG. And the end of the any protein will have one of these three codons, UAA or UAG or UGA. Okay, so once in the ribosome itself, when the messenger RNA is translated into a protein, if one of these codon is found, then that is a signal that to stop making the protein, that's the end of the protein, release it for the functionality of the body. And I hope I made it a little clear for you how this central dogma goes on. So let's talk about the Rhd gene. As I told you, Rhd gene can give a direct protein because Rh antigen is actually a direct protein product from the gene itself because it's a protein. Now, one thing which I want you to concentrate is the Rhd gene has 10 exons. Of course, the Rhce also, because if you see the Rh gene itself, both Rhd and Rhce, they are opposite, they run opposite each other, as Dr. Khalid rightly said. All right. So if we go and see the exons that the coding sequence, I said, the exons of the coding sequence of the exon, they have 10 exons. Each gene has, of course, different exons, but for the Rhd and Rhce, they have 10 exons. So you have exon 1, 2, 3, 4, up to 10. And these exons, now when they are translated into a protein, they are actually 417 amino acid long that are found on the surface of the red blood cells. So this is how they look on the red blood cells. As you can see, they have like short loops, all right, 6 loops at the exterior part of the red blood cells, and they have loops at interior parts, which is in the cytoplasm itself. So, but at the end, what I want to say is this is 417 amino acids for both Rhd and Rhce protein. Both of them are 417 amino acid long. Now, what I have done, I have now blasted this is actually protein blast. So these are the protein, the 417 amino acids that shared between Rhd and Rhce. If you can notice from this figure, most of the amino acids are same except those that I highlighted. All right, so there are only, I think, 37 amino acid difference between Rhd and Rhc. They are very similar to each other. It's like 96% they are similar to each other. All right, and I have also here, as Dr. Khalid also said, and as I have said also, that the Rhce can be big C, little c, big E, little e. So now the difference between big C and little e can be also seen as here, just one amino acid here, one amino acid here, one amino acid here, and the difference between the big E and small e is just one amino acid. All right, so this is just a blasting of the amino acid sequence between Rhd and Rhce and what are the differences between them. Now, if we talk about the protein itself, the protein nature itself, this is one of the pictures which was shown by Dr. Khalid as well. What we did, we have modified this from, of course, Professor Bill Flagel, who has published this in 2007. But what we did, we have modified that by adding the name of the amino acids in each of these, and these black amino acid are the differences between the Rhd and Rhce, as you can see from the figure itself. So of course, the antibody will always react at the exterior part, which is this part of the protein. All right. So now different commercially available antisera are used to detect D antigen. I'm talking about D antigen here. all right? So different antisera that can react differently with this D antigen. Now, and the ability to detect varies. Maybe one antisera will give you a strong 4+ reaction, and one antisera can give you even 1+ reaction. So the ability of the detection between antisera varies. However, but eventual report is either D positive or D negative. This is what we want, either D positive or D negative. Now, since our case is actually a D negative case, I'm just going to concentrate today about serological D negative case. So now serological D negative, if we take it, we have either false D negative or true D negative. If we talk about false D negative, few D variants can give false D negative, which is a problematic sometimes, especially in donor. In donor, you need to report the D stats correctly. So these D variants can cause a problem especially in blood bank. All right. So let's talk about this false D negative first, and then we go to the true D negative part of it. So what are these D variants? Of course, the Rhd gene, as Dr. Khalid said, it's highly polymorphic. So that means it has different forms. All right, that's why it's highly polymorphic. Okay, and now because of these different alleles that can give a different Rhd shape or a different Rhd look, okay, presence of these alleles can affect the Rhd antigen on the red blood cells as a quantity or a quality. So the quantity is the number. It can affect the number of the D antigens on the red blood cells. And if we talk about the quality, if you go back to the immunology itself, we talk generally when we said antibody reacts with antigen, but actually antibody reacts with epitope on the antigen itself. So the quality is this. Now, some D variants affect the epitopes. Now, if we take it into grant that Rhd antigen have different epitopes, like if I give you an example, 9 epitopes. Now, some D variants will have only 6 epitopes. So D antigen is present, but the epitopes are affected. So that's why it's called the quality itself. When we talk about quantities now, D variants are actually, if we list the D variants types, D variant can be weak D, del phenotype, or partial D. All right. Now, this weak D, if we talk about the quantity, the number of the D antigens are affected, we will be talking mainly about weak D and del phenotype. And usually the mutation affects, either the mutation will be at the amino acid change will be either at sites where there is a transmembrane structure on the red blood cells, or it will be in this histosol site, in the cytoplasm site. So this is where the mutation can take place for weak D and del. That's why the presence of weak D and del affect the quantity. These mutations anywhere over there, it will affect the number of the D antigens on the red blood cells. Now, when we talk about the quality, like in what you get in partial D, the effect of the amino acid or amino acid change will be at the external part of the protein where antibody and antigen react. So this is the part where partial D variants can exist. Okay, the mutation of partial D, mainly what I would say, this is mainly. So let's talk about this false D negative as some researchers they did regarding these D variants. Now, in our research, which is done in California, at least 120 weak D or del donors typed D negative. See, they have been typed D negative, though they are D positive actually, okay? And they have been transfused to D negative donors annually. So this is an article published in 2006. In another study by Dr. Bill Flegel, okay, in 2009, which was a big sample size for 46,133 serologically D negative donors. The Rhd genotyping showed that 96 samples had Rhd gene. See, now they are D negative, but they have the gene. Okay, and half of them, they had the Del phenotype, which is a D positive actually. Another study on partial D, which is in Tunisia, all right, Musa and his colleagues in 2012, what they found, one sample, which is DBT, that's the partial D, was mistyped as D negative. So can you see now, we have a lot of cases where weak D and Del phenotype and partial D can be serologically. May I kindly ask you to please unmute the mic? So that was for the false D negative. So this is what I was saying. False D negative is because of the D variants, which can give the mistyping of the D, the actual D status of the donor or the patient. Now let's talk about the true D negative. Now when we talk about true D negative means it might have the D gene present on the DNA itself, but it might be not active as well. But let's talk about the true D negative. What is true D negative? It has three reasons. One is complete Rhd gene deletion, one is called hybrid gene, and one is called pseudo gene. Let's talk about complete Rhd gene deletion. Now, since I have explained the basic molecular biology, so this is what exactly means the complete Rhd gene deletion, as Dr. Khalid even said. All right. So this is the locus of Rhd gene, as you can see here, there is no exons, no Rhd exons at all here. So there is deletion, the complete deletion of Rh. This is of course Rhce, but this is Rhd. There is complete deletion of Rhd exon, and therefore there will be no D antigen. So that's in normal circumstances where you don't have the gene, you don't have the product. All right. So this is what I can say. This is the homozygosity. So both, of course, as you know, each individual has one chromosome from mother, one chromosome from father. So now both of them lacks the D gene. So that's why it's called homozygous. No Rhd gene, homozygous here. So this haplotype is actually, one of them is DCE, the other is DCE, and therefore the individual is actually DCE. Okay, D, of course, no D with little c and little e. So this type of complete gene deletion usually found in Caucasians, but I have read one recent article which was published in Iran. It was in 2019, I guess, if I'm not mistaken. And even Iranian, like 99% of Iranian who are D negative, actually they are negative for the complete deletion of the Rhd gene, which is quite odd, to be honest, because as we know now, this type of gene deletion is famous in Caucasian, but it has not been studied well in Middle East, so that's why it could be one of the reasons. Anyhow, let's go to the second part of the true D negative, which is second example, which is hybrid gene. What is this hybrid gene actually? The hybrid gene, this is of course the Rhd gene, and this is the Rhce gene. Now, for the expression of little c and little e, there is a specific amino acid at the location 300. Of course, I told you the amino acid long, both antigens or proteins are actually 417 amino acid long. So amino acid number 336 has to be glycine here, and amino acid 245 has to be leucine here. So if this is the case, then the Rhce gene will express little c and little e on as a gene. But in the case of the hybrid Rhd CE, now, as you can see here, the amino acid 245 has been, first of all, replaced or has changed to amino acid valine. Okay, and the amino acid 336 has been changed to cysteine. All right, so now these two changes in the amino acid has given a product, the same little c and little e, but this minor s means they are partial. So this is one of the things, Dr. Khalid, maybe it needs to be investigated whether your patient in case 1 or case 2, whatever you said in your presentation, some of the people, they have the partial antigens. So one of the things now to see whether they have these hybrid Rhd CE antigen on their genes in the sequencing of the DNA itself. Anyhow, and so this is regarding the RHCE, which has the partial small c and partial small e. Now, if you see the Rhd gene, you can find that small amount of RHCE is also replacing the RHDE. If you see these pink boxes are RHD. Now, if you can see in this hybrid gene, small amount of exon 3, exon 4, exon 5, 6, and 7 is replaced with RHCE. So that's why it's called hybrid. It's a mix of RHD, CE, and then D again. So this is D, this is D, and in between there is CE. All right. So this is the case in this type of hybrid. But again, whenever there is a replacement of RHCE in RHD, the mutation also exists, what we have seen here, okay, the cysteine and valine. All right, and because of that, there will be, because of this hybrid, there will be no D antigen, and with this there will be big C but partial. And this is one of the things, Dr. Khalid, as you said, somebody has big C and he has also anti-big C in the serum. So this is one of the cases that should be studied. If this patient has the hybrid type of the gene, okay, because this type of the gene can produce partial C, and if it's not compensated with the other dose of capital C, then this individual can produce anti-big C, though he has big C in his red blood cells. So the haplotype here is actually no D, but he has big C, little c, and little e. Let's talk about the Rhd Soda Gene, which is the case report which we have found in Oman in one of the donors. Now, what is this Rhd Soda Gene? Now, Rhd Soda Gene is something where the Rhd exons are full. You will find full exons 1 to 10. However, there is addition of 37 base pair or 37 nucleotides. 19 of these nucleotides in the intron 3, this is where intron 3 found, okay? And 18, the remaining 18 nucleotide will be addition in exon 4. So that's 37. So 19 will be in intron 3 and 18 will be in exon 4. So there is addition of 37 amino acids, 37 nucleotides, addition of 37 nucleotides in the gene. So this is a big amount of nucleotides has been added in the Rhd gene. So in addition to all of that, you have also a mutation of some nucleotides in exon 4, exon 5, and exon 6. But eventually, because of all of these mutation and addition, you will have the Rhd gene that is inactive. It is not active. Though there is a full gene, but it is inactive. So that's why we call it Rhd positive haplotype, because it has the full gene, but D negative. It gives no D antigen because it is inactive. It cannot produce the D antigen itself. All right. So the question is here, why Rhd Soda Gene is inactive in Rhd gene? And the answer for that is this: the addition of this 37 base pair insertion. Remember, I told you each three nucleotide will give you one amino acid. Now imagine you have 37 insertion, 37 new nucleotides, which can give you new amino acids in addition to what it's supposed to have. But because of that, this is something called a frame shift. This frame shift, what it will do, this addition of 37 base pair, it will introduce one stop codon in exon 6. So the normal Rhd gene supposed to have a stop codon by the end of exon 10. So all the exon is translated into protein. But because of this addition, the stop codon, the signal for the body to stop making the protein, will be in exon 6. So that's why there will be no Rhd protein synthesis. So that is actually the Rhd pseudo gene. Pseudo means it's not, it looks like there is a full gene, but actually it's not giving the antigen. So that's why it's called a pseudo gene. So when you analyze the gene of the individual with this Rhd Soda Gene, you will find the full Rhd exons from 1 to 10. But actually, in the messenger RNA, it's not translated as a full, as a stop codon will be in exon 6, stopping the protein from, stopping the gene to produce its actual or wild type protein. So the case reports, in our case here in Oman, one of the donors was Rhd Soda Gene. So the 43 years old BRHD negative Omani blood donor, okay, who passed all eligibility criteria test and donated blood. And his Rh phenotyping was, of course, he had only little c and little e, that's it. So initially, if we take it from the phenotype, his genotype is like that: small d, little c, little d, little c, little e, all right? Now, doing the molecular analysis of this donor, we found that he has all Rhd exons except exon 5. I'm going to explain this later. Except exon 5. I said in my previous slide, it has all the exons, but in this patient, or in this donor, it's missing. Rhd exon 5 is missing. I'm going to explain this later. Okay, but please keep in your mind this. The sequencing of these Rhd exons ruled out any D variants. So we have ruled out the D variants. So it is not a false D negative. What we found in the sequencing, we have found that there is 37 base pair insertion. And we have found also a mutation in the same exon 4609, and guanine has been changed to adenine. So this is typical pseudogene mutation, which we found. What we suggested, this is African Rhd genotype responsible for the serological D negative, actually. And I explained why it gives D negative, and I said because the protein is not, it's incomplete and it's not giving the actual D protein. Then, so because the serological D negative was considered as a true D negative, therefore we have said that this is actually not a small d, little c, and little d haplotype, but it's actually, there is a D gene. So that's why the haplotype has been changed to a big D, because there is existence of the D, but it's not functional. It is inactive. Now let's analyze the case. There is no amplification of Rhd exon 5. Why we haven't got amplification of Rhd exon 5? we actually used allele-specific primer, and this allele-specific primers, of course, this is for the amplification of the DNA. All right. So this allele-specific primer that targets actually the wild type Rhd exon 5, and the wild type Rhd exon 5 at position 655 654. Okay, the nucleotide should be T. All right. Now, because of the existence of the Soda gene, the same position nucleotide has changed to cytosine C. All right. And therefore, because of this primer, the specific primer, recognize only this T here and not C. And because Soda gene has this mutation here, that's why our used primer couldn't recognize our Rhd exon 5, and it didn't amplify it. And the conclusion is this from the Rhd exon 5 is present, but our used primer did not amplify it because of the reason which I have already explained. So Rhd exon 4 primer, which we use actually, can amplify both the normal type of Rhd exon as well as the Soda gene type. So we used a primer, okay, from Professor Neil Event, who has actually designed these primers, and we used from this actually from his paper, this type of primer which can amplify both genes. If you have Rhd exon 4, normal Rhd exon 4 wild type, it will amplify it. And if you have even Soda gene, it will amplify it. But of course, we wanted to further explore the product which we got, okay? And then we sequenced that, and we found that it has 37 base pair insertion, okay, and as well as the mutation associated with Soda gene in the exon 4, which is 609. Now, this is what we found when we blasted. Of course, the sequence which we in the sequences we took the DNA, the nucleotide sequence, and then we put it in NCBI blast. All right, and we found that this is what we found. If you can see here. Now the sequence here, this is our sequence, this is query, this is our sequence. It starts at nucleotide 37. That means it didn't recognize nucleotide 1 to 36 here. It didn't recognize. Now, but it has given here that you have additional 37 nucleotide, and this confirms our finding that we have 37 base pair addition, all right, in this donor. And of course, if you see here, this is the mutation which which I told you, 609 mutation, where the guanine is replaced with adenine. That's typical associated with Soda gene. And this is, though the resolution is not good enough, but this is the mutation which we found while we analyzed the sequencing results. So this is the A, where it's supposed to be G actually in normal condition. So because this is what we if we are trying to make it in a schematic diagram, so this is what we have seen, because we didn't have the primers to study the mutations associated in exon 7 as well, and the exon 5 as well, because exon 5, we couldn't amplify exon 5. So we just could confirm the finding of this Soda gene by sequencing exon 4 and exon 6. And therefore, this is what we got now in our case. And we concluded that this donor has actually D gene with small c and small e antigen, and therefore the haplotype is actually not small d, little c, little a, but it's actually a big D. So what we have recommended here to do the zygosity testing. Now the zygosity testing is very important to understand now as you know, we have, of course, we have two genes, two chromosomes from each individual. So two genes. Now, if this donor is homozygous for both Soda gene or not, we don't know, because we need to do this zygosity testing. Or this donor is actually in one gene is actually a Soda gene, and the other gene is actually a complete deletion, and this is called hemizygous. Whether this patient a hemizygous here, okay? So we couldn't find this, okay? So that's why we recommended a zygosity testing to be done for this type of cases. So at least we know whether we are dealing with homozygous or we are dealing with hemizygous case. So in conclusion, our observation drives us to realize that the necessity to study the molecular background of the negative phenotype in Omanis. And this is what I have done actually, and maybe we'll publish this in course due maybe in 1 month. I'm going to publish that. And of course, we have done also a study, okay, on the frequency of the negative phenotype in Omanis, and we found that Omanis, they have 8.35% negative. So 8.35% of D negative, that's a lot actually. So actually we need to do the molecular background of D negative, which we have done actually, and we will publish it soon, inshallah. The molecular basis of zygosity determination would be a good approach to further explore any cases related to D negative. And thank you very much for your listening. And if you have any question, maybe we, of course, as we know, we have a 15-minute session or 20-minute session of questions. You can ask any simple questions, not difficult one. Thank you very much. Thanks a lot. So Dr. Zainab, maybe Dr. Zainab, if she's here. Dr. Zainab, are you there?
Sorry, Dr. Mujtaba. Hello.
Yes, I can hear you.
I was just disconnected.
I am done with the presentation, Dr. Zainab.
I was unmute. No, I was there till the end, but I was trying to unmute to talk, and then it was disconnected.
All right, then. Thank you.
So thank you, Dr. Mujtaba, for the fruitful presentation. And I think everyone learned a lot from the two presentations. They were excellent. Now we have time for questions. Please, to all audience, please ask any questions. We have like maybe we can make it 10 minutes for questions. I think yes.
Yes.
Maybe if the voice is not possible, then any questions can be written. We can see then the questions. If you can write them down. Anybody, if he has or she has a question.
I think this is Raya. We need Raya. You can go to the chat section and put your question, please.
Okay. Yes, Dr. Zainab.
Yes.
Good morning, everyone. My question is both of you. It's one question, but one part for Dr. Mujtaba and another part for Dr. Khalid. Okay, if we have, my question is, first of all, thank you very much for a very deep and comprehensive presentation regarding molecular basis of the antigens. But my question here, if we have discrepancies between genotyping and serological results. So the decision here to make in transfusion practice regarding my question to Dr. Mujtaba, if the donor and serologically it's negative. And we, at the same time, if we can get the molecular testing of that donor, which showing these variants or genotyping positive or the presence of gene. So how we really can take the decision to label the donor. This is your part. For Dr. Khalid, the decision of to transfuse the patient with a variant antigens, especially if the patient is negative for antibody screen, there's no underlying antibodies, and you have both these results, serological and genotyping, but there's a discrepancy. So how you can make a decision? Thank you.
All right, Dr. Khalid, would you want to start or do you want me to start?
It's okay, Dr. Mujtaba, you can go ahead.
All right, okay. So thank you very much, Raya, for your question. Now, in most of the literature, if you go, now it's been agreed that the molecular genotyping overcome the serological limitation. So I would suggest to go for genotyping, all right? Now, if the genotyping shows there is a D gene, all right, and of course, the knowledge is required, of course, to decide whether this is inactive or active gene whatsoever. Based on that, then it has to be either D positive or D negative based on the genotyping results. This is my suggestion. Yeah.
So we have to label the donors D positive?
Yeah.
If we have both this result?
Have to report as D positive. Yeah.
Okay.
Except, of course, if the donor is Soda gene, like this case, so he's D negative actually, because his gene is inactive actually. He doesn't produce any antigen. So that's why I said the knowledge is required in this case now to decide whether you are dealing with inactive gene or it's an actual gene itself.
Okay, if it is really an active gene, but serological we miss, we don't have facility for genotyping, and we label that donor is O negative. If that unit transfused to the O negative patients, can this patient develop anti-D, for example?
It can give a high risk of alloimmunization. Yes, unfortunately, yeah.
Okay.
Okay, so I think I can answer your second question, Raya. And again, as Dr. Mujtaba said, the molecular studies will be very helpful and adjunctive to the serology. However, I think my answer will not be, it's not as easy or straightforward as we think. Most of these molecular results comes actually from a problem that happened to a patient developing some weird, unexpected antibody. And that's a way of answering or resolving the issue. And that's clearly the genotype will give you the answer that this is a partial antigen, and that's why the patient developed the antibody. And from now on, you really have to give him antigen negative. However, when we face patients with multiple variant alleles, including 3 or 4 antigens sometimes involved, here the situation becomes more difficult. There are some experts who would suggest finding a donor that is genotype similar. That's as you can see is not easy or straightforward. However, we always take the safest approach. There are many things we know today, but there are I think more things that we don't know yet. And one of the things that we don't know yet, which of these partial antigens actually is more sensitive to develop antibodies. Not all patients with partial antigens do develop alloantibodies. Why? We don't know. That's the case is very well known for the Rhd gene now for many years. Now for the Rhd gene, the situation is quite similar. There are variant alleles that produce antibodies and have been reported to produce antibodies. And for those, based on the literature review, you really have to give them antigen negative based on your genotyping results. Others, if you face difficulties, you have to prioritize your options because sickle cell disease patients often come on urgent basis requiring blood. and it's not always readily available to find a genotype matched blood for them.
Yeah. So it'll be easy to depend on serological results only.
As far as it works well for you without, but when you face a problem with a patient that you cannot answer simply with serological testing, that's where the genotyping comes in place. And if it is available more for patients and donors, then more answers will be available for your hands to give it for your patient. That's why the literature now is promoting that this genotyping testing to be used more and more, not only for patients, but for donors as well.
I have just to add one thing more. I do agree with Dr. Khalid actually with what he said, and I just want to add that there are kits actually. There are kits that are available to genotype the weak D, partial D, and even D zygosity, and they are actually available. The company name, if I'm not mistaken, Rhd Gene. They are called Rhd Gene kit. They are from Germany actually. All right. I have studied these kits actually, and unfortunately, because of the mutations in Omanis, these kits are not, of course, I'm not recommending these kits to be used for Omani population because of the mutation they have. So there are kits that are available actually, okay, to detect all of these genes actually, all right, these alleles in Rhd gene. But again, I'm telling you, as Dr. Khalid said, this is based on some experience, like maybe in Caucasians, okay?
Yeah.
So that's why they have made these kits available, but that doesn't mean it can be used in Oman. So that's why we need to establish our own system, how to phenotype.
But just to add one thing, I think okay, I agree with you. Maybe by using, if you're going to use these kits, maybe you're going to lose a lot of our negative donors, I think, because of all this. Just go for deep molecular testing, and we can detect, for example, active gene of D. I think there will be there will be a risk of losing a lot of our donors with the D negative.
Yes, that's correct. But again, as Dr. Khalid also said, that not all of them also will develop, like maybe only 15 to 20% only develop antibodies. But the reason is not known actually. Why? If you give sometimes a positive red blood cell, D positive red blood cell to a D negative, they might not even produce antibodies. So everything has its own advantage and disadvantage.
Thank you very much, Dr. Khalid and Dr. Mushtaba.
Thanks.
Thank you, Ryan.
Any other question?
I do have a question for Dr. Mushtaba, actually. Perhaps I missed this, but I wonder what triggered all the investigation in this donor, since he was apparently serologically D negative. So what went wrong to necessitate the investigations?
This is simply the simple answer for that. That was my thesis actually. So that's why I was investigating the molecular background of D negative Omanis. That's why.
Okay, so he was part of a larger study, and that's what you found.
It was a part of my study. I thought I will share it as a case study.
Yes, excellent. Yeah. Good work always results in some interesting findings.
Yes, of course. I do agree indeed.
Yes.
Any other questions?
Okay, Dr. Mushtaba, Dr. Khalid, thank you very much. If we don't have any more questions, we would like to conclude this webinar. And thank you, everyone, for attendance. Okay, thank you.
Thanks a lot.
Thank you, Dr. Zain.
Thank you. Bye.